Good afternoon, everyone. Before we get started, let us first offer a prayer for the success of this webinar.
Again, good afternoon, everyone. Welcome to the Meet the IAU Astronomer program. First, let me introduce myself. My name is Justin D. Castillo.
And I am Julian Delda from the Space Science and Astronomy section of PAGASA.
The Meet the IAU Astronomer is a program offered for free by the International Astronomical Union-Office for Astronomy Outreach, aiming to connect teachers, informal educators, and amateur astronomer groups with IAU-member astronomers through a virtual presentation. With this being said, we would like to welcome the teachers, students, organizations, and our colleagues from PAGASA that are present here today.
Before we get started, we would like to go over a few reminders for everyone to participate actively in today's event. First, as displayed in the slides shown prior to the start of the webinar, we would like to remind everyone to please mute your microphones, turn off your cameras, and pin the speaker screen once the speaker starts the presentation. This is to avoid unnecessary distractions.
Also, participants will have the opportunity to submit text questions to our presenter by typing the questions into the question box in the Google Meet control panel. You may send in your questions in any time during the presentation. We'll collect this and address them during the Q&A session at the end of today's presentation. You will also have the opportunity to ask your questions directly to our presenter. Just raise your hand, state your name, affiliation, and question once we open the Q&A session.
Lastly, we will be providing a certificate of attendance to those who will stay with us until the end of the program. We will be also sending the link to the survey on the presentation and we would appreciate it if you will complete that and provide your feedback.
To formally begin our program, let us hear from Dr. Esperanza O. Cayanan, PAGASA's Deputy Administrator for Research and Development, for her opening remarks.
Thank you very much. Distinguished guests, ladies and gentlemen, a pleasant day to everyone. On behalf of our Administrator, Dr. Vicente B. Malano, and the whole of DOST PAGASA, I cordially welcome everybody to this awesome event to witness a spectacular lecture on astronomy by an internationally well-known astronomer, Dr. Diana Besliu-Ionescu from the Astronomical Institute of the Romanian Academy. We at PAGASA are very grateful to her for sparing us her precious time to share her knowledge and expertise in this field. We are also delighted and thankful to all the participants composed of teachers, educators, science-related undergraduate students, and astronomy organization members. PAGASA is very honored to virtual meet a renowned social physicist through the International Astronomical Union-Astronomer program that is offered for free by the Office of the Astronomy Outreach of the IAU. This is one of the 3 virtual meetings that we will be hosting, of course, with the help of IAU and OAO. Early this year, PAGASA has been active in and popularizing astronomy through various social media platforms. The annual National Astronomy Week on the 3rd week of February was celebrated by uploading informative videos and publication materials through PAGASA Facebook page. This was highlighted by the podcast episode on common astronomy myths and misconceptions and the mobile phone astrophotography contest open to the public. The Global Astronomy Month 2021 last April, which is an annual worldwide celebration offered for astronomy enthusiasts, was celebrated by posting educational videos and materials. Highlighting the event was the podcast episode about frequently asked questions on astronomy. Today, we have invited huge crowd to virtually meet and hear an interesting talk from Dr. Diana entitled The Sun and Its Impact on Earth. The Meet the IAU Astronomer program aims to connect teachers, informal educators, amateur astronomy group, children, adults, and other members of the public with IAU-member astronomer by virtual meeting. It also offers multitude of scientific topics, including astronomical research topics, importance of astronomy for society, choosing astronomy as a profession, to name a few. Aside from Dr. Diana, we also have requested to host 2 more virtual meetings with IAU astronomers. We hope that our participants today will also look forward to join the next virtual meetings. So without further delay, I am really very excited for this event today. Let us all enjoy and learn from our special speaker this afternoon, Dr. Diana. Thank you and mabuhay.
Thank you, Dr. Cayanan. Now, without further ado, may we call on Ms. Maria Rosario C. Ramos, the IAU National Outreach Coordinator for the Philippines, and the officer in charge of the Space Science and Astronomy section to introduce our speaker for today.
Thank you, Julie. Dr. Cayanan, Dr. Servando, colleagues, and participants, good afternoon. It is a great honor to introduce one of the women in astronomy who is part of the IAU Astronomer program of the Office of Astronomy Outreach. Our invited astronomer grew up in Romania. She can speak native Romanian, English, and French. She is a graduate of Bachelor of Science in Physics at the University of Bucharest, major in spectroscopy, plasma, lasers, and optics. She finished her doctoral philosophy degree at Monash University in Australia with a specialization in astrophysics. Her computational skills are in Bash, IDL, Python, and C language, to name a few. Part of her blossoming career in physics, she was a physics teacher from 2001 to 2005. And through her outstanding work on solar physics, she worked as a solar astronomer at the Astronomical Institute of the Romanian Academy from 2003 to 2009. She is also a solar astronomer at the Institute of Geodynamics of the Romanian Academy in 2009 to present. In 2017 to present, she also works as a solar astronomer at the Astronomical Institute of Romanian Academy as a researcher 3. She actively participated in national research projects in Romania. She is also part of the European Space Agency projects contract and the Romanian contribution to the PROBA ASPIICS Instrument Science Operations Center development for 1 year as a principal investigator. Most of her works are on solar and heliospheric researches. Her most cited publications are Seismic Emission from M9.5 class solar flare, published in Springer Nature in 2006. Helioseismic Analysis of Solar Flare Induced Sunquake in January 15, 2005, and was published in Monthly Notices of the Royal Astronomical Society in January 2007. All in all, she has 14 publications with a total of 109 citations. I know that you are all excited to meet and hear from our invited astronomer. Please join me in welcoming Dr. Diana Ionescu of Romania, who will talk on the sun and its impact on Earth. Dr. Diana, the floor is yours now.
Thank you so Thank you so much for this beautiful introduction. I feel like I've done too much. I actually haven't done that much. I'd like to thank the organizers first for the invitation and for this opportunity to talk to your institute and everybody that has joined this presentation. And of course, the AIU office that has facilitated this meeting. So I will start sharing the screen so that we can see the presentation. Is it working? No. Okay, just a second. Is it on now?
Okay, it's okay.
Yes.
Okay, thank you so much for the confirmation. So I will talk today, as already been mentioned, about the sun and its impact on Earth. I will not be able to see the messages. If you have any messages during the talk, hopefully maybe chat or somebody else will read them at the end or in between. I've noticed that the audio connection is a bit flawless, so if I don't hear you, please repeat that again. So if you notice that I am not stopping from talking, probably I haven't heard you. So I am mostly researching within the Astronomical Institute of the Romanian Academy. I am also a member of the National Committee for Astronomy, and obviously a member in the AIU Committee for Astronomy Outreach. What will we start today with is a very general presentation of the sun. I like the images that represent to scale the sun. So the first slide that we had today was the sun to scale, because I've worked a lot with adolescents, let's say teenagers, that usually have this impression that they are everything. And I really like to emphasize that we, all of us, are here. And actually, this is the sun. So the sun is a bit larger than us, although it's a normal median middle life aged star. It's also a very little star, as we can see on the right side of the slide, where there is an image that compares the sun as size with some other stars. And in here we can actually see the sun that is the smallest compared to all the stars within here. Actually, this is a good star, because it provides us obviously with everything we need, like the heat and the light, without which we could not exist here. So, to talk a bit about the structure of the sun. The sun is structured in layers. So we'll talk about firstly of the layers within the interior, and then going up in the atmosphere, and we'll present the exterior layers. So within beneath the surface that we can see with the, let's say, neutral filter, there are three layers: the core, which is the innermost layer, then the radiative zone, and lastly the convective zone. What do they differ mostly from? It's the mechanism that the energy is transported or produced. The core of the sun is a powerful nuclear plant, right? It produces energy, it produces photons. It is the core that fuels the entire sun. Inside the core, we suppose we have something like a million degrees, so that the fusion is available. And here it's the layer that, as I already said, produces all of the energy. The density here is extremely high, and then it slowly decreases towards the outer layers. The radiative zone, which is a bit less dense, obviously, than the nucleus, differs from the core because of the mechanism that the energy transports itself. So here, the energy radiates from the core towards the convective zone. The next zone is the convective zone, the right beneath the surface zone, where the convection starts to happen. So the convection would mean that we will start to see movement of the plasma. So the plasma is let's say near the radiative zone. It is heated. Then the plasma, because it's heated, it's rising up, and then once it reaches the surface, it will give the energy away, and then it will go down once more. That's why near the surface we will see excuse me, we will see a movement that resembles something that boils, something like beans, or a bit under pressure, let's say soup. Just before we go to describing the layer, the surface layer of the sun, I would like to emphasize an aspect that has astonished me at the time I was learning it. How long does it take for a photon to escape? This question actually has two different parts, let's say. For a photon to escape, the photosphere. So for a photon to reach us from the surface of the sun to us, it's actually around 8 minutes. And I think that's common knowledge and nobody can question that, right? But then how long does it take for a photon to escape the nucleus, the place where it's actually produced? So this is an image that represents how a photon is the path of the photon within the interior of the sun. Because the sun is so dense, especially in the nucleus, especially in the core, in this side, it will not be able to move a lot. It will only move this mean free path, which is, if you see here, of an order of 10 to minus 5 meters. That is actually less than a millimeter. It's actually 0.3 micrometers. So that's undistinguishable by eye, right? We cannot see the distance that a photon is walking before being hit by something else. So because of this, the photon will actually be absorbed and emitted and will have a really random and chaotic path until it will reach a much a less denser layer, so that it can escape and it can reach the photosphere and escape the sun. So using this mean free path here, we can approximate that the time that it takes a photon to move through the entire radius of the sun. The radius is approximately 700,000 kilometers, let's say 695,000 to be more precise, but that's not that precise either. So it's of an order of 10 to 13 seconds. How many is that in years? It's approximately 1 million years. So what the photons that have reached us today have been produced about 1 million years ago. So it actually this is actually a bit debatable. It depends on how many approximations, or exactly which approximations do we take into account when considering this path. But it's been arguable in the science committee, that in the science world, that this is at least 10,000 years and probably at most 1 million years. So this is one of the facts that I think it's striking for us, knowing facts about the sun. Then once it has reached the photosphere, what does it happen? What do we see? Because we actually can see only the outer layers, right? So in this image, we have the sun structure. In the upper image, we have the interior sun structure that we have just presented in another form, and then the outer layers in the lower part. So the first layer that we see when we look at the sun with the neutral observer, with the normal filter, let's say a G-band filter, it is the photosphere. This is a fragment of the photosphere. It's an image taken by the satellite SOHO with one of its instruments. And you can see here some spots. Spots are some active regions that appear darker because they have a lower temperature. Why do they have a lower temperature? Because there is some magnetic field here that inhibits the local movement of the plasma, which I'll show just a bit later. Therefore, this will emit less light than the surrounding regions. Next to the photosphere, so just going a bit upper in the atmosphere of the sun, we can see a layer that is called chromosphere. Now, this is a layer that is a bit less dense than the photosphere. It's a bit harder to see. We cannot see this without special filters on telescopes. And this will show something like a filament. I think you can see here a darker region, or the normal quiet sun regions that show the plasma movement. Also, starting with the chromosphere and rising up in the corona, we can see some structures that are called coronal holes. These structures are less dense. They have high magnetic field, and they produce continuous currents. This is one of the main sources for the currents in the solar wind. Sorry. And then this really thin layer, thin as we can't see it properly, is the corona of the sun. This is an image taken with an extreme violet telescope, and once a flare happens, some loops, specific region of the sun will heat up and will make the respective magnetic loops collide, and then will explode, will eject some material that will probably integrate into the solar wind later on. You can also see in the upper side of the image, besides the structure of the interior and a bit of the chromosphere on the side, you can see a proeminence. That is the same structure as the filament that is visible here, but it's seen on the projection because it's upper, it's higher than the limb, so we can see it as a structure, as a separate structure. Now, one of the things that have been really talked about during this last month was the first light of the Dick's telescope. It is an American telescope founded by the National Science Foundation. It's a huge telescope with a 4-meter mirror, and it has already gathered this image. This image shows us very clear the granulation, that movement that happens on the photospheric layer. So the photosphere was that first layer that we can actually see with the naked eye, let's say, not the naked eye, with the neutral filter. With the solar eclipse glasses, we can't look at the sun directly, right? Or we can look just once and then we'll lose our eyes, let's say. That was something like a joke at the time where we had the eclipse here. So here you can see exactly how chaotic the structure of the photosphere is, rather than the nice image that we have here. Here you could not have noticed that movement start with such a precision or with such an accuracy as we can see in these biggest movies. I put on the right side of the image the former best telescope, as far as I can see, as far as I know. It was also a ground telescope, the Dutch Open Telescope, where you can also see the granulation. But the resolution, I think it's obvious that the Dick's resolution is by far higher. What area of the sun is comprised here? It's almost 20,000 kilometers on the x-axis and about 10,000 kilometers on the y-axis. I'm not sure if that astonishes you, but when I started my PhD, you could only see, I don't know, about 1 megameter pixel or something like that. This is by far an improved quality of the images. What was, let's also run the movie, because this is an animation of the granulation, so that you will see the movement of the granulation in time. So the time is specified here. I haven't run it very, very fast so that everybody can follow the movement. So this, in here there is the time. So each bubble has a lifetime of rising, expanding, and then disappearing back into the photosphere. What is was also seen for the first time is with this accuracy were these bright points. So you see, in certain points within the granulation, there are bright structures. You can see a few in the dot images, but they do not appear as clearly, and they are not as fine and refined as in the Dick's images. And actually, I would like to emphasize that this was, I think, the first confirmation for what I didn't obviously, what researchers have seen in the MHD simulations. So there is a group of researchers in Norway that has some extremely nice simulations. I think there's a paper back in 2004 that has already presented some granulation, and they had these bright points appearing within the bubbles, within these bubbles. And at that time, we did not have the confirmation of physical observations, and now we do. So what's left is a good explanation for these for their appearances. Moving on, it's still not still. It's one of the main structure, one of the main characteristic of the sun. It's that its activity is cyclic. What does it mean? That it starts from something low, it raises, and then it goes back to something high. So on the left side, we have three graphical representations, three different graphical representations of what a solar cycle means. And in here, we have the total group number. So group number is a number that characterizes the active regions that are seen on the sun. So those, let's go back a bit so that I can confirm. One more. So those regions are being counted, measured, and then calibrated into one formula, and there's a number that is produced. And there is the SIDC center affiliated with ROB that gives a smoothed sunspot number. That is the number that we have recordings from even before 1800s. But that number depended on the acuity, let's say, on the perspective of the observer. So that number actually differed if we had two different observers calculating that number. And in 2015, this group from ROB has uniformed the entire sunspot series. So we currently have a calibrated, a very reliable sunspot series that clearly describes the solar cycles. So these are the solar cycles, and in this graph, besides the total number of of the groups. The groups can be can be counted differently considering their hemisphere. So some of the groups appear in the northern hemisphere of the sun, some of the groups appear on the southern hemisphere of the sun. And this is what this graph represents here. We have just left solar cycle 24 and we are starting in the solar cycle 25. We just had an X-type solar flare last week. I think if it's not the first, it's the second, but I think it's the first solar flare from this solar cycle. It was spectacular, but unfortunately it was a bit close to the solar limb, so we could not see it very nicely. That was just a side story to the solar cycle activity. What is the main feature of this activity? Solar cycles are not alike, right? Although they should last for around 11 years, if you can approximate the distance between these the year marks, they can be shorter, something like 9 years. I think this one is the shortest one. Or they can be longer, around 13 years, and I think this one is the longest. What you can also see here is that they vary in intensity. So some of these solar cycles are more active than others. Why is that? That means that a particular solar cycle had more active regions rather than the other. And we actually don't know why, or it's not universally accepted why this is happening. The second graph here shows basically the same thing, but each point is representing the sunspot with its latitude, so and its date. So what we can see here is that sunspots at the beginning of the cycle appear higher with higher latitude, and then their latitude decreases. So at the end of the cycle, they are very close to the equator. This is actually one of the two methods to separate the spots from one cycle to the other. And the last graph here is an interpretation of the mean latitude. So this does not differentiate between the southern hemisphere and the northern hemisphere. It's just to show the things that I've just said, that the sunspots start at higher latitude and then they end at lower latitudes. On the right side of the slide, we have a very nice composite of some SOHO images. They are in the extreme ultraviolet line, and they have chosen one image representative for each year, so that we can see that higher activity means actually higher temperatures and higher and more active regions, so that the corona looks light up compared to a solar minimum, right? So I was just saying that we have finished solar cycle 24, so we can see less activity. We should start to see some activity in the next few years, and obviously reaching the maximum in probably 5 years or so. This slide was chosen for us discussing eruptive phenomena. So up to here, I only mentioned briefly a solar flare in the solar wind, but the sun has more than just these events, right? So this is a composite image of running differences from an extreme ultraviolet image inside. So this is the contour of the sun, and then and also running differences for the corona. What we will see, because I will let it run again, excuse me, is a solar flare igniting somewhere around here, and then a following coronal mass ejection exploding around the sun. So I let it run again to start again from the beginning. So here is the beginning. Then you will see, I hope this does not cover exactly the region. It should be just beneath. The flare should happen just above my cursor. So there is an ignition. There is a heat up of the local plasma, and then that plasma rises up into the atmosphere, and then produces this very beautiful coronal mass ejection. I will stop this animation here so that you will see the structure of it. This is what we call a full halo CME, and these are important because seeing in a detector something that completely fills the detector means that this could reach the Earth. So once this ejection is formed and it is filling the Glasgow image, there is a high probability that this will reach the Earth. And on the right-hand side, there is a simulation that has been run by the group. It's an NLIL simulation. They are running an MHD 3D simulation that actually show the CME how that little bubble that we saw here evolves in the space and was hitting the Earth that is here and propagates further on into the heliosphere. So this is let's say a top view, and that would be a side view for the propagation of the CME. So this was related with one of the, I think it is the most or the second most powerful geomagnetic storm that we had during the solar cycle 24. So this is why CMEs are important, because they can reach the Earth and influence the magnetic field of the Earth and produce geomagnetic storms. I will stop the simulation and try to move on to the next slide, which is an artistic view of what we have just seen in the slide before. Space weather is a general term that covers a lot of things. It should include all the solar events that could influence the state of the magnetic field on Earth. It's an image, obviously not to scale. It also shows two satellites, two ESA satellites. This would be the representation of the CME that we just seen. And this is what is our most precious shield. This is the magnetosphere that is shielding us from most of the sun radiation, right? Because the sun radiates in all wavelengths, and some of the radiation, not all of it, but some of it, it's deflected by this shield that we have here. And as you can see, the magnetosphere is smaller. I can't find a better word for it. It's smaller on the day side, and it's larger and elongated on the night side, because as the solar wind comes, it will bend and tilt the magnetosphere and will create this form. Although for us on Earth, we will see differently, right? Because the Earth will keep spinning. The magnetosphere will be not, let's not say stable, but will have this shape no matter what. Okay, so going into details into space weather effects, what we have here, we have three images of the sun that we have talked about. The photosphere with some spots, with some active regions here, then the corona with CME in happening, and EUV image of the corona with the solar flare igniting here. So starting with an solar active region, right? Because if we don't have an active region, we will probably not have any space weather, or space weather will be very low. We can have coronal mass ejections that will interact with the magnetic field, with the interplanetary magnetic field, and in some conditions, basically when the southward component will be aligned with the magnetic orientation of the CME, will produce a geomagnetic storm. Also, coronal mass ejection can produce energetic particles that will move obviously faster and will produce solar radiation storms. On the other hand, we could just have a solar flare and not have a CME associated. This is actually an interesting aspect that I haven't mentioned, that not all solar flares have CMEs and not all CMEs are associated with flares. There are associations, obviously, as I shown, but not all of them are correlated. Although they seem to be the same aspect of some magnetic involvement of the local structures, they look and behave very differently. Okay, so from a solar flare, we could have an increased X-ray flux, such as I said about the solar X flare. We can record that on Earth. We can see a spike within the integrated X-ray flare, which can produce a radio blackout, for example, or they can also produce energetic particles that will also lead to a radiation storm, but will have different energies than the ones produced by the CMEs. On the right-hand side, it's again an artistic view of these effects of what is the sun producing: coronal mass ejections, solar flares, radiation, or solar energetic protons on top of the cosmic rays that may come from outer space, that will affect astronomers that are in the space, will affect satellites that are gravitating around us, will damage the not damage, let's say, will disturb the atmosphere with different layers and in different with different aspects. Then they could have an impact on aviation, or the signal that a satellite receiver should exchange with the satellite, and so on. These are going to be presented in detail, not much detail, so that we won't bore the audience too much. So one of the first examples of an impact of the solar weather is the producing of geomagnetically induced currents. They are produced once the magnetosphere has been charged, or has been its magnetic field has been increased in such a way that it will induce a current on Earth. So this is the magnetic disturbance, let's say. So right, I hope you can see here that there's the variation of the measurement of the magnetic field in time for an event that it's famous, for a series of events that have been famous and have been very discussed in the literature. They are called the Halloween events. They started on the 28th of October 2003 and ended around 4th November. It comprised a series of powerful flares, amongst which we believe what would have been the most powerful solar X flare on the 4th of November, but that was also on the limb of the sun, and it was not directed towards Earth, and in such a way we still have recorded the most powerful flux ever. So going back to these currents, we see the spikes of the variations in magnetic field, and for these spikes we can compute the currents. What the intensity of a current, of a damaging current, is around here. So you can see the amps per second here. This have been computed for the same event. What I've shown on the right hand side are some geomagnetically induced currents that are being computed, I think daily, within the working hours, using the ESA space weather portal. So ESA has a pretty comprehensive portal that is divided in specific domains: solar, heliosphere, ionosphere, geomagnetic storms, and so on. And you can find there a lot of information, including these currents that are being computed for the day that the observations are done. Another example of impact of the solar, of the space weather on our daily life, because our daily life have become extremely technological, is the impact on communication. So once the solar flux is exceeding some, let's say, background limit, right? So these are some radio fluxes measured on Earth, so that these are not satellite data, correlated with a decrease in the signal of the GPS. So if the signal of the GPS will decrease, we will actually obviously lose the connection with the satellite, or we will have an error in measuring our position. I think everybody uses, let's say, Waze or Google Maps to find their way. But if your car is not positioned in the correct spot, you will not have the correct path, right? And this can happen once a solar storm is, a geomagnetic storm is on, let's say it like that. Then another example of the impact of the space weather is its damages, or its how it affects the satellite infrastructures. So there is this thing that is called satellite anomalies. I'm not sure. I think they count everything that is happening, which is not supposed to be happening, as an anomaly. So let's say a charge of a detector, or a wrong measurement of some particular data. And this is the anomaly number per each year, associate or overplotted with the sunspot number. So what is remarkable here it's that although the highest activity cycle was around 2000, the highest anomalies were here. This is a very interesting discussion, and it's an entire topic within the science community. What is the most geo-effective event related to the sun? I'm not sure if that's visible. I've also added the citation for each slide. I forgot to mention that. So each slide had the paper that I have found the specific graph in. So if anybody wants more detail about that specific subject, just look up the paper and you'll see everything in there. Another example is how the space weather impacts the aviation, right? So I believe that by now everybody knows that the radiation has an impact on the body. No matter what life we have, some level of radiation we will accumulate. And I will start with the right-hand side. There's a table that specifies the level of the dosages that are acceptable and not acceptable. So the redder we go, it's the worse that we can get. So to fatal death within weeks, right? So we can start with a normal dental X-ray and a chest X-ray, right? I think everybody knows that we are not supposed to have more than 2 X-rays because of the pandemic. Probably everybody has been through that. This is a normal radiation that we're all exposed to per year. And then this is a full dose in CT scans. And then these numbers are for various things that we can experience, like radiotherapy and stuff like that. And these are obviously with risks because the radiation will accumulate. This is just to give you a measure of these numbers, to give you an idea of the numbers. And then on these two graphs, we have the radiation doses computed for 2 space flights, one from Sofia to Praga and one from Los Angeles to JFK. I can't remember. JFK airport. And both of them show, so the flights are what, a few hours? Both of them show that the population within these flights have a dose, an increased dose within a very short period of time, exactly correlated and because of that solar event. So this is how much damage space weather can done even to our daily life, not only to the astronauts that are exposed or they have accepted that they expose themselves to the radiation, but to us that we are not always aware that this radiation can also affect us. Moving on next. I wanted to show you a comparison between the 2 solar cycles that have already ended. So we cannot state anything yet about the solar cycle 25 except for prognosis of how active it will be. To show you the sunspot number, the blue line is the yearly smoothed sunspot number, the red line is the monthly smoothed sunspot number, compared with the number of CMEs, I think it's here. And then the same thing for solar cycle 24. What is to see here? That the solar cycle 24 was less active than solar cycle 23. And these can also be seen here in measuring or in interpreting the strongest geomagnetic storm That was this one associated with November 20, 2003, compared to March 17, 2015. What did I use to compare geomagnetic storms? I used an index, a geomagnetic index that is called the DST, disturbance storm time. Its minimum value, it is usually used to describe a geomagnetic storm. There are many geomagnetic indices, but each one is calculated differently. So for me, it says that it describes different state of the magnetosphere. The DST index is computed using 4 observatories close to the equator, so they have low latitudes. So if a low latitude observatory records a geomagnetic storm, I definitely know that that is a geomagnetic storm, because definitely on the poles it will be a stronger geomagnetic disturbance than the equator, right? Because of the image of the magnetosphere that I've shown at the beginning. So this is why I usually use the DST when comparing the impact of the space weather. Then I've also added here something about the latest geomagnetic disturbance. It was something of a rather moderate storm, and storms are classified as weak, moderate, intense, or super intense, giving some limits to this index. Okay, this is what the last slide about the impact, where we compared the solar cycle as activity with the total number of the CMEs, black bars, and the geo-effective CMEs, red bars. So, because these are all relative numbers, so they all should represent similar things. So what is here to see is that we have a lot of CMEs, out of which very few are geo-effective, right? So about what is the 3% out of the total number of CMEs are geo-effective, right? A maximum of, and the same thing happened for the solar cycle 24. However, these geo-effective CMEs are those that we are trying to understand, that we are trying to predict, as we will see on the next few slides, because those are the ones that directly affect our lives. So, how will we establish the CME if a CME is geo-effective? We would be interested in its direction. Is it directed towards Earth, or is it going someplace else? What will be the travel time? How many days it will take to reach us? I think the shortest time between a CME and a geomagnetic storm is around 15 hours. It's actually less than a day, and the longest is around 5 days. It will or it will not produce a geomagnetic storm. That is actually the main question. And then a secondary question, but not as important as this one, how intense will be the geomagnetic, how large will be the geomagnetic storm? On the table here, you have a sample of what I used as a database in the study that I will mention in the next 2 slides, that we have gathered from 2 catalogs, from the ICME catalog that lists interplanetary coronal mass ejections. So it's a catalog that show properties for CMEs that have reached the interplanetary space, correlated with CMEs, so for which we actually know which CME have have started that ICME. And we used a logistic regression model proposed by Srivastava. I won't get into much details. I would only specify that she used 7 variables that were related to measurements from the CME and ICMEs, and used the sigmoid function with this composition of the properties, and then produced a probability that a certain CME will or will not produce a geomagnetic storm. What we have tried in 2 different studies was to increase the database so that we would predict more than just intense and super intense geomagnetic storms. So that would be this study. This study was focused on the ascending phase of the solar cycle 24. And we had 10 independent variables also related to the solar source. And then we actually wanted to do a bit of a different aspect of this prediction, to only use the instant exclusively CME data that we can gather at the time of the observation of the CME, and try to see if we can predict, if we can give a correct probability that that CME will produce or not produce a geomagnetic storm. These are different methods of applying the regression. I won't get into that detail. If anybody wants to ask, we'll have a separate discussion. These are the success rates for the 2 models. So this is for the 2019 model, and this is for this year's model. So this year we have actually improved the model that has predicted, the model has been able to correctly predict the observed geomagnetic storms, something that we haven't correctly done or with such an accuracy before. Okay, this I believe is the last slide that is showing what is the sun like today. Unfortunately, the sun today is very quiet. I'm really sorry. I have close to nothing to show you, but I will present the each image, at least what you can see in each image, so that you can look it up when there will be something to see. So the first image, this one is the continuum. So it's the neutral image that we would see with using solar eclipse glasses. The next image is a colorized version of a magnetogram. A magnetogram shows the local intensity of the magnetic field. So in this image, we can actually see that there is some activity here and here, but that means that it's not enough to produce a sunspot. So the local inhibit of the movement is not enough to cool the region of the photosphere. Then the next slide, the next image is a Dopplergram that shows a map of the local speed, of the local velocity in the photosphere. Then that's an image of the chromosphere. And then this is again a lower, somewhere in between the photosphere and the chromosphere. And then we go up in the corona, and we can actually see that there is associated with this more intense magnetic field, that there is some activity that is visible in the corona. What else is very nice to see is that these black spots here are the coronal holes that I've mentioned a bit earlier, that are producing the solar wind. the continuous solar wind that hits the Earth. So at the end, I would like to acknowledge some of my funding that produced part of the results that I have very briefly presented here. And then to thank again the organizers for this opportunity and the nice way that we have collaborated, and to thank everybody for the attention. And I am waiting for your questions. Thank you.
Thank you very much, Dr. Diana. I hope you all enjoyed this inspiring presentation. We will go ahead and take some time for the Q&A session. This is your chance to personally ask your questions to Dr. Diana. So just raise your hand, state your name and affiliation, and then you can ask your question. So now we're open. You can press the raise hand button on your Google Meet screen. So we see a question in the Q&A box. Mr. Christian Jericho Tagalog, do you want to ask your question personally or will just read it from the Q&A box?
Please read it.
Okay. So question to Dr. Diana. On a sun expert's perspective, do you think it's possible to terraform Venus and Mars given its closer and further proximity relative to the sun?
Yes. to a very brief answer, yes. From this perspective, yes. But there are many aspects here that some other specialists should contribute here. So it's not only the sun that will affect this terraforming, obviously. But from my perspective, yes, that is possible.
Okay, thank you, Mr. Christian, for that question, and I hope Dr. Diana answered your question. So, anyone else? Okay, from my co-host, Julie.
Thank you, Justin. Hi, Dr. Diana. Once again, thank you for your presentation. And we would like to listen to your experiences as you work as a solar physicist. Can you give us some advice to those who want to become like you? She has left the meeting. I guess Dr. Diana has left the meeting, but we'll just wait for a few minutes. Maybe she will come back. So how are you guys? How's the webinar so far? Thank you, Sir Christian. Yes, it's great actually learning about the sun. And yeah, while waiting for Dr. Diana, siguro we can talk about some of her talks earlier. Diba? When you observe the photons of the sun, you're actually looking back in time. Diba? Imagine it took for about 1,000,000 years diba, bago natin ma-observe before we can observe the photons. Yes, hi Dr. Diana,
I
you're
am
back.
so sorry. Yeah, I'm so sorry. That was a question and I lost connection.
It's okay.
It's
Okay,
okay.
what was the question?
We're back.
Yeah, We just want to know what are your advice to those who want to be a solar physicist like you?
Oh, okay. So to be a solar physicist, yeah, it's a lot of work. I don't think you can do solar physics without computing nowadays. At the beginning, I did not have that in mind, but I think you either had to be extremely bright so that you would have extremely nice theoretical ideas, or medium bright and then combine that with the IT skills and have some models or test your hypothesis and propose an aspect. It's a really good field to be in because of the increased interest towards space weather. And the main source of the space weather obviously remains the sun. So if anybody is looking for a career in this domain, yes, I think it's a good career, and it will be at least for the next decade of future, because we still have a lot of satellites that are going into the space within the next years or so. So we will test different technologies and different observations that will add to our knowledge. And actually, I would like to mention that, especially if you have young people amongst you, even nowadays, we have a lot of data. There is too much data that it's not enough analyzed. So if you can find an international group or by yourself to find a subject or some data that you would really like and have some interpretation, have some analysis on it, probably someone will be interested in seeing that result.
Thank you, Dr. Diana.
So there are some people who sent questions again in our Q&A box from Mr. Bon Lozano. Will there be an instance in the future, or maybe if it happened in the past, where CMEs and solar storms will have or had a catastrophic effect on Earth?
Yes, yes, yes. There have been, yes. There have been. So it's actually the first event that was analyzed as association between a solar event and the geomagnetic storm. It was the Carrington event. It was an event that happened in 1859, and it was the first time that the sun was being observed within continuums, so within that white light that those images. And the observers have seen a white flare. A white light flare means an extremely powerful flare, because usually, or what I have shown in the slides, were flares igniting in the EUV. So they are not that heated up. But if a flare has a signature lower in the close to the photosphere, and such a signature that it's visible as a white light, that is a very powerful event. So to our knowledge, that is the strongest event as a solar event, but we do not have the technology to measure it. So there are papers that estimate how powerful that solar flare event was. And to come to the second part, it was the first time that that flare was associated with Earth effects. So they had a power, not a power plant. They had a geomagnetic storm recorded in the magnetic measurements. So this is why we know that it's happening, and they had disturbances, I think, in the what do they call that, telegraphic signal. So that was, to our knowledge, the biggest, largest, and the most impact. Other than that, we know of some, I don't know, I think 1989, there was a large power failure in Quebec also because of a geomagnetic storm, but I'm not sure about the source of that geomagnetic storm. And an aviatic incident, I don't know, November 2015 or something like that, when Norway canceled some flights because of the disturbances within the magnetic field, and obviously they can't fly without knowing exactly positions and other measurements.
Okay, thank you, Dr. Diana, for that answer. So we have one question from the chat box. Could we predict major and catastrophic GS based on historical data? And this is also connected to a question I want you to answer. So based on your studies, do you see a trend on the solar cycles when solar activities are much stronger or weaker, so that maybe we can prepare for them in the future?
The current solar cycle is predicted to be medium towards low active. The state of the prediction of the geomagnetic storm is not that advanced. So I just had a student that has finished her bachelor actually trying to better improve this prediction. At the moment, I don't think we can predict. I mean, I think we have to change our perspective, because we do not predict with exact, with enough accuracy to correctly predict when a geomagnetic storm will happen. However, if we use the data from the satellites like ACE, which are in Lagrangian point 1, so they are close to Earth, there are formulas that will correctly, almost accurately predict the magnitude of the DST index. Well, magnitude is wrongly said because it should be a negative value, but I think you get the idea. But that, from Lagrangian point 1 to actually recording the storm on Earth, is just a few hours. That gives us enough time to, let's say, stop a power plant, or stop the, I don't know, the train, or stop the transportation of the gas, but it will not give us time to put the astronomer inside the space station, or inside the, you know, they have some rooms that are better shielded than others. Will not give us time to turn away the satellite so that it will not be directly impacted from that. So this is why everybody is looking into the CMEs and how to correctly predict the CMEs. The main problem that I haven't talked here is not only how or when we're exactly describing the CME, but the interaction of the CME with the interplanetary plasma, because the CME will overimpose on some pre-existing solar wind. How will that interact? It will be deflected, it will be accelerated, decelerated. It will help that CME reach Earth correctly, or it will bend it such that it will not. So there are a lot of aspects, and this is why this field is emerging and is of extreme importance at the moment. But we cannot have a definite answer at this time for this question.
Okay, thank you again, Dr. Diana. So there are some more questions. These are connected questions. So when do you think in the future time will our sun fade, or its sun's rays go low towards its influence on us here on Earth and all the planets in the solar system? So talking about the end of the life of our sun.
Oh,
So,
the end of the life of the sun, 4 and about half million years. So it's way, way, way further. By then, either we will not be here, either we will not be here. I mean, either the humanity will have found a way to travel to some other place, either we will have been extinct. So it's not our problem, really, really. It's really not our problem. We are exactly at the middle life of the star. I'm not sure if I said that at the beginning.
Thank you, Dr. Diana. Another question from Jeremy Chamboy. Could we safely collect CME, or I think the data itself, and probably use it for future technology?
Could we what?
Safely collect CME and probably use it, the data for CME, and probably use it for future technology.
I see the question now.
Yeah,
The energies.
yes.
Oh, that is a very good question. I have no idea. Um, Theoretically, it should be possible. Yes, theoretically, it should be possible. I mean, I don't see from a theoretical point of view something that would stop us. Practically, it will stop us because we do not have the technology to to store such an energy. I'm not sure how we would. Maybe probably in doctors. Okay, so it's doable, but I don't think that now if because if it would have been possible now, it would have been done. But theoretically, yes, it's possible.
Thank you for that answer. And one of our last questions in the Q&A box from Carmiel Pasadilla. How is the atmospheric dynamo or the giant electric current in the sky driven by the sun?
In the sky, I am not aware of a dynamo in the sky. I'm sorry. I know about the dynamo of the sun that actually is producing the magnetic field of the sun, but I'm not sure how to answer that question. Probably it's something else that means to be asked, but I can't see it.
Okay, thank you, Dr. Diana. So, guys, do you still have any questions? Okay. It looks like we have covered all of your questions. So, is there anything else you wanted to cover, Dr. Diana, before wrapping up? Or
No,
any last messages?
just thanking everybody for this nice opportunity and this the nice ambience that have been they have been here. Thank you for the questions, really interesting questions. It's actually, I think it's the first time that I have so many questions on the impact rather than the sun. Usually people ask me about the sun, but it's really nice to have been here. So thank you for this opportunity, for organizing, especially chat. Thank you. And maybe we will see some other time. We will see us some other time. Maybe in person, God, given this pandemic will disappear at some point.
Thank you.
Great. Thank you again, Dr. Diana.
Okay, thank you.
Yeah. Thank you for your great presentation, and it was a pleasure being with you today.
Thank you.
So we will now proceed with the awarding of the Certificate of Appreciation to our IAU astronomer, Dr. Diana Besliu-Ionescu.
Thank
So I will read the certificate. Department of Science and Technology, Philippine Atmospheric, Geophysical, and Astronomical Services Administration, Certificate of Appreciation is awarded to Diana Besliu-Ionescu, PhD, in grateful recognition for sharing her expertise on solar physics during the IAU-OAO Meet the IAU Astronomer program held via Google Meet on 9th July 2021, given this 9th day of July 2021. Signed by Vicente B. Malano, PhD, PAGASA Administrator. Thank you for sharing your knowledge with us, Dr. Diana.
Thank you.
Thank you, Dr. Diana. And to our participants, you can now access the link to the survey form sent in the chat box. Please accomplish the form by 7 p.m. A certificate of attendance will be emailed to you shortly. Thank you for sharing your time with us.
Okay.
Photo opportunity, please, bago sila umalis.
Okay. Thank you,
Uh,
everybody, and goodbye.
okay. I mean, Dr. Diana, we would like to have a photo
Oh,
opportunity
possible.
with you first.
Okay.
So, guys, we would like to request everyone to turn on their cameras for our group photo. And don't forget to give your biggest smile.
Smile!
Next.
Next group, please. Smile. Just smile.
Tell us if you're already finished.
Okay, thank you, everyone. You may turn off your cameras now again. So at this junction, we will hear a closing message from the Chief of the Research and Development and Training Division, Dr. Nathaniel T. Servando.
Good day to everyone. Um, Good afternoon here in the Philippines and good morning in Romania. I hope you enjoyed the informative discussion today. Before we formally close this afternoon's program, I'd like to take this opportunity to express our profound gratitude to our eminent resource speaker, Dr. Diana Besliu-Ionescu, for her very enlightening talk and for unselfishly sharing her expertise. I am certain that all of us who attended her lecture learned a lot from it. I am very delighted with the active and dynamic participation of the attendees, not only from PAGASA personnel, but from participants from different schools as well, making this event very successful. I would like to also express our sincere thanks to the International Astronomical Union, particularly the Office for Astronomy Outreach, for initiating programs like this today's event, meeting the IAU Astronomer. That provided a chance for astronomy enthusiasts to meet, learn, and be inspired by the IAU astronomers via a virtual platform, considering the current global health crisis. And for allowing us to host not only one, but 3 virtual meetings. And last but not the least, I want to commend the efforts and hard work of the personnel from the Space Science and Astronomy section of the R&D and Training Division of PAGASA for organizing and hosting this event. And of course, the support of the PAGASA management, headed by our administrator, Dr. Vicente Malano, and Dr. Esperanza Kayanan, Deputy Administrator for R&D, who gave us an opening statement earlier. I hope that the succeeding virtual meetings with the IAU astronomers will be as fruitful as this one. Quite a unique lecture talking about space weather, particularly the scientific aspects, and of course the hazards associated with the unusual sun's activity, like CMEs. So enjoy the rest of the day and have a pleasant good afternoon once again, and stay safe always. Thank you
Thank you,
very much.
Dr. Servando. So this concludes our webinar. Thank you all for attending. Again, we have set the link to the survey on the presentation in the chat box. We will be also sending this link to your email. Once done with the survey, you will be receiving your certificate of attendance.
Again, we hope you have learned a lot and enjoyed this presentation. We appreciate you all being here.
On behalf of PAGASA and Dr. Diana, thank you for joining us today. Enjoy the rest of the day and we will see you next time. Happy weekend!
weekend!
Thank you, Dr.
Thank you.
Diana.
Goodbye. Thank you.
Dr.
Goodbye.
you.
Diana.
Bye.
Thank you so
Thank
much,
you,
Dr. Diana.
Diana.
Thank you, everyone. Bye.
Bye.